Okay, so what I will talk today is about what makes a good proxy reward function, and the guiding application is going to be post-training of language models. So fortunately for me, language models don't really need much introduction, but for our purposes, to be clear, this is just a neural network that gives us a distribution over sequences of tokens. Okay, and we're going to denote it by pi theta. Theta is the parameters that we learn. And what we can do is we can give our model some prompt x. This is a sequence of tokens, and it gives us a distribution over possible outputs y. And the typical development pipeline of language models these days consists of two main phases. Okay, the first one is called pre-training, and this is where you teach the language model about general world and language knowledge. Okay, this is done by you training it to predict the next token over vast amounts of data, the type that you can find on the internet. Now, after pre-training, the second main phase is called post-training. Yes, we're in this weird phase in the terminology where we no longer train models, we just pre-train them and then jump to post-training. But either way, the idea is that in this phase, you take your language model, which is very good at predicting the next token based on statistics from the internet, and you turn it into a useful AI system. Okay, here you train it to solve different tasks, you can try to align it with human preferences, and there are different components in this phase, and one of the major ones is reinforcement learning, where instead of giving the model examples, you give it tasks in the prompt. Okay, this can be a math question, and you let it try and solve it. It produces outputs y, and you train it based on some reward signal that it receives. Okay, there are different types of methods for reinforcement learning. The one which is standard for training language models is called policy grading. Okay, this just amounts to you're maximizing the expected reward using gradient-based updates. Okay, very simple. So we have some set of prompts S. Your objective here is V. This is the value function, the expected reward. And you're taking gradient updates with respect to theta. Okay, where pi theta is the language model. In this context, it is also called the policy. So when I say policy, what I mean in this talk is just the language model. I'm going to use this interchangeably. Ideally, what we would hope to do is we want to maximize some ground truth reward which exactly captures the intended behavior to what we want to teach the model. But the unfortunate reality is that it is rarely possible to specify or compute such ground truth rewards. And so we have to resort to imperfect proxy reward functions. And the primary example here can be alignment. Okay, we want to align the language model with human feedback. The underlying assumption that there exists some ground truth reward that governs at least some aspects of human preferences, but we don't really know what it is. And what we do instead is we train proxy reward models. We train neural networks over preference data that was labeled from humans, and then we use this proxy reward model to align our language model. In other domains beyond alignment, such as math and coding, which are considered these days as verifiable domains, the rewards that we use are often also imperfect proxies. Okay, ideally, we would like some reward function that exactly verifies all steps in the output. For example, if you solve a math problem, but this is very difficult to do in standard settings, so we often resort to just verifying that the final answer is correct, if we can do that. And in code, often we just use unit tests, which can be okay, but is also fundamentally incomplete. Okay, and these are just 3 examples. Beyond that, proxy reward functions are really prevalent, also in other reinforcement learning settings, unrelated to language models. But it is actually not well understood what makes a good proxy reward function. Okay? The most well-known potential consequence of using a proxy reward is reward hacking. Okay, this is a well-known phenomenon, which is initially, if you train with a proxy reward, everything might be going well. Okay, you increase both the proxy and the ground truth. But at some time point, you may start, even though you keep increasing the proxy reward, the ground truth reward may start decreasing. Okay, this is because there's a mismatch between these two reward functions. So although you're increasing your proxy reward, you're no longer doing better in the actual task that you care about. And due to this risk of reward hacking, the conventional wisdom about how you should evaluate proxy reward functions and the way that this is done in practice is that they should not deviate much from the ground truth reward. Okay, the closer the proxy reward function is to the ground truth reward, it's considered better. And the underlying assumption, okay, so any deviation is harmful, or at least you should try to minimize deviations. And there can be different measures that you can think of. The one that people typically use in practice is accuracy, at least in the setting of evaluating reward models for language model alignment. Okay, accuracy, this measures how well the reward function ranks different outputs. Okay, you have some data set of preferences. This means that each example is a triplet. You have a prompt and two outputs. And the label that you get is which output is preferred. Here, y plus is preferred over y minus. Okay, and this corresponds to formally that y plus has a higher ground truth reward. In practice, you just ask human labelers to tell you which one they prefer. And then accuracy is just a fraction of examples in this data set that the proxy reward function ranks correctly. Okay, and existing benchmarks for reward models in the context of alignment, they measure exactly this. Okay, they give you a list of which reward model is more accurate over their fixed data set of preferences. Okay, so this is the state of affairs, which corresponds to we try to find proxy reward models that are closest, hopefully, to the ground truth. And this raises the question of whether is this really what we should be doing? Okay, is it true that more accurate proxy rewards are necessarily better? And yeah, is there a question?
You know, the previous slide, the y plus and y minus are their outputs of the learned LLM, the post LLM, that then someone tells it was right or wrong, or something you do before and you compare your results to?
Yeah, it's a good question. So you can get these outputs by sampling them from your current model. This is something that people often do. You can also just get them from anywhere that you want. So there are different ways that you can create this data. The bottom line is you get outputs from different sources, and then you ask people to label which one they prefer. Okay. Right. So what we're going to see in this talk is that actually more accurate proxy rewards are not necessarily better. And the way that we're going to see this is by taking an optimization perspective on what makes a good reward function. Okay, we're going to consider how fast does the ground truth reward increase when we maximize a proxy reward function, okay, through policy gradient. And we're going to focus on two main limitations of accuracy and more broadly evaluating a proxy reward according to how much it deviates from the ground truth. The first is that even if a proxy reward is very accurate, it can still induce a very poor objective landscape for policy gradient methods. Okay, so accuracy doesn't capture every aspect of what makes a good reward function. And the second limitation will be that actually not all deviations from the ground truth are equal or even necessarily harmful. Okay, this is the plan for this talk, and we're going to elaborate on both of these points. Where in the first part, we're going to talk about the role of reward variance in policy gradient optimization, and this is based on two papers, the first done at Apple and the second at Princeton. Okay, are there any questions about the introduction before we dive into the details? Okay, great. So first, a technical slide. This is the setting in which we do our theoretical analysis. I need to give you two things here. Okay, first is what is the parameterization of the policies that we're going to consider, and the second, what is the training algorithm exactly? Okay, so for the policy parameterization, the first kind that we consider is a very general family. Pretty much captures any standard language model these days. Okay, the way that they produce a distribution over outputs is they decompose it into a product of next token probabilities, and then each probability for the next token is just a softmax over a vector of logits, and the way that you get this vector is through some parameterized function f theta. This can be your favorite neural network, it can be a transformer, it can be anything else. We only need it to be differentiable with respect to theta. Okay, and this parameterization, what we can prove for it is lower bounds on optimization time. So that lower bound that I'm going to show soon will apply to this very general class of policies. The other class of policies that we're going to consider is a more simplified one, is what is sometimes known as a linear softmax policy. What it means is that the logit of an output y is just a linear function of some feature vector. So each output is associated with a feature vector. This matrix phi contains rows. Each row is a feature vector for an output. And then you just take a softmax of the logits and you get your probabilities. Okay? So it's a simplified model. And the reason that we need to analyze it as opposed to this very general function class is that when you try to prove upper bounds in optimization and that actually succeeds, unfortunately, in the worst case, this is not possible. And you need to add some structure. And so the results I'm going to show where we prove separation between optimization time, then this will be to this class of functions. Again, it's worth highlighting that despite perhaps its apparent simplicity, the objective for linear softmax policies is not concave. Again, it's actually quite complex, and it's still an active area of research to better understand optimization for even this class of functions and policy group methods. Okay, so this is the policy parameterizations, and the second thing is the training algorithm. The analysis that I'm going to present is going to be for gradient flow. This is a continuous version of gradient ascent. Essentially, it corresponds to gradient ascent with a very small learning rate. And the motivation behind analyzing this is that post-training is usually done through small learning rates. Okay, so it can model this and simplify the analysis, but I'd say that it's pretty straightforward to extend all the results I'm going to show to gradient ascent with a small finite learning rate. It just adds some complexities. Okay, and lastly, what I'd like to remark is that we're maximizing the expected proxy reward, but what we really care about, right, is the expected ground truth reward. Okay? All right, so that's it. That's setting. You don't really have to memorize this, but just in case you want to have in the back of your mind what is the exact technical details of the policy that we analyze. Now, the quantity that is going to be important here is the reward variance. It's a very simple quantity, pretty much what it sounds like. This is the variance that our proxy reward function induces for our policy and a prompt. Okay, the randomness here is with respect to outputs sampled from the policy. The reward function is deterministic. Okay, to estimate this, all you need to do is you sample multiple outputs from your policy, compute the reward, and then estimate the variance. As simple as that. And here's the exact definition, just to be clear about what is going on. It's the standard definition of variance, nothing special going on here. Okay, and the way that you can interpret this from the perspective of the reward function, reward variance captures how well it separates different outputs that are probable under our policy. Okay, if it separates them well enough, then the variance will be high. But if it gives roughly the same reward to all outputs that our policy is likely to produce, then the variance is low. Another way that you can think of this is some form of margin. Okay? And this is in contrast to accuracy, which disregards completely this degree of separation. Okay, accuracy only depends on how the proxy reward function ranks different outputs. So accuracy and reward variance effectively capture different aspects of the reward function. Okay, and what we prove is that reward variance turns out to be intimately connected with policy gradient optimization. Okay, specifically when it is low, it will take us a long time to increase the reward. Okay, we prove that the time it takes for the expected proxy and ground truth rewards to increase by any desired amount, okay, by any additive constant, it grows inversely with the initial reward variance. Okay, here you have an average over the training set of prompts and the variance of the reward with respect to the initial policy. And there's an inverse relation here. Okay, the exact power is not super important. What it is that the lower the initial reward variance is, the longer it will take us to increase the reward. And yes, is there a question?
What is just number or function of time? Like if you keep training your classic reinforcement learning, the reward changes.
Yes. So the variance depends on the policy. So over time, the policy will be different and the reward variance will change. Right? So this result shows that if initially it is low, then it will take you a long time. And it's true that throughout training it can change. And why does this happen? Okay, so it turns out that the gradient of the objective, of the expected reward, it vanishes whenever the reward variance is low. Okay, this is a new connection that we make between reward variance and the landscape of policy gradient methods. We also show that this reward variance will not increase fast through time if it starts slow, and because of that, you're effectively stuck in this very flat area of the landscape. And it takes you a long time to escape. And I'll say that I'm giving this result in the context of language models, but it applies much more broadly. Pretty much to any reinforcement learning setting where you have a policy that produces a distribution over outputs through the softmax function. Okay, the reason that this occurs is due to the geometry of the landscape that the softmax function induces. Right? And for our purposes, what it implies is a necessary condition for what makes a good reward function. Okay, we need the proxy reward to induce sufficient variance if we want to have efficient optimization. Okay, and as you might have noticed, accuracy doesn't appear in this slide. Okay, this result doesn't depend on how accurate the reward function is. And we can use this to prove that more accurate reward functions are not necessarily better, in the sense that for any initial policy, you can have a perfectly accurate reward function, and on the other hand, a relatively inaccurate one. Okay, it still needs to get some pairs of outputs correctly, but can get most of them wrong. And yet, if you train with the perfectly accurate reward function, the ground truth reward will increase arbitrarily slowly. Okay, so it'll be better in some sense to use the imperfect proxy reward function. And here I'm giving this extreme case of perfectly accurate versus inaccurate, but more broadly, we show that optimization speed can be independent of accuracy. Okay, for any accuracy value that you give me, there can be a reward function that works well, and another that works poorly. And I think it's best to understand this through an illustration, and this is going to be a proof by picture of sorts. Okay, so on the left, what you see here is the ground truth reward function. This is what we want to maximize. And we start from this gray dot here. This is the initial policy. To maximize it, we need to go to the top left. Now for the proxy reward function, accuracy and reward variance, they capture distinct properties. Accuracy roughly translates to how well does the reward function agree with the ground truth on which directions are good. If it is very accurate, it will also tell us go to the top left, which is great. But if it is inaccurate, it may tell us to go to some other direction, which is actually poor under the ground truth. And this is what can lead to reward hacking. But even if the reward function is perfectly accurate, it can induce low reward variance. And in this case, what our results prove is that you're stuck in this very flat area of the objective landscape, and it will take you a long time to escape. And in contrast, you can have a less accurate reward function. It still needs to identify good directions, but it can be less accurate. And if it induces a higher variance, it will lead to faster increase in the ground truth. Okay, so this is the essence behind the results I just showed.
How is accuracy? What is accuracy in this picture? So whether
So accuracy is
accuracy depends which triplets you give me.
right. So
what should I think of it?
yeah, in practice, it's over some fixed data set. But the theory is just you can imagine any distribution. You can assume it's accuracy over the population. So it's not a fact that you don't have coverage in a data set, and this is what creates this. Accuracy is just take any distribution, take the uniform distribution over all outputs, and just a fraction of outputs that you ran correctly, for example. And like these results, they hold for any distribution that you choose.
Yeah, because I think if you just take over a fixed set, then the result is trivial because you can
yeah, like an output that's not in the set. Yeah, but it's not what's happening. So this is for like the theory is for whatever distribution that you give. Yeah, it's basically due to the fact that accuracy doesn't capture the flatness of the objective. It captures something about which outputs are good, but it doesn't tell you everything about how well policy grain will work. Right?
And the flatness is also the speed and the flatness. It depends exactly on how you do the step size.
Exactly. So here, the gradient vanishes with the reward variance and also higher order derivatives. Now, for a fixed step size, you're stuck. You can try to do more clever adaptive schemes. It's not clear which work in theory. There is a method to solve this in theory, but it is not practical. It's called natural policy grain. It's a clever preconditioning scheme, but to compute this preconditioning, you can't really do that in practice. So, like, there is a solution in theory to this, but it's not. There's not a solution that is practical that I'm aware. Yeah, so it definitely depends on how you do the optimization. But for standard methods, you have this issue.
So you have fixed step size. You can just multiply the reward function by a very small constant, and you'll never optimize fixed step size. It's not right. It's not a trivial.
No, so like whatever fixed, like even if it's a large step size, yeah, but of course it depends.
If I know the step size you do, and I'll just multiply everything by
yeah, but
small number, you'll never move.
Right, so we can like one way to escape our lower bound. Okay, you can do a huge step size, or maybe just multiply the reward by 1,000,000. But okay, you escape the lower bound, but you don't really get the faster optimization for free. You just get instability. Right. So the question is like, for some reasonable step size and some bounded rewards, yeah, if the reward match is low, you get stuck.
You just could add a random noise, right? So low variance is a sign of bad proxy, but high variance is not.
Yes. So this is a necessary condition. It doesn't necessarily mean that having maximal variance is best. It just means that if you have a low variance, that's better. Okay, and you can see this in practice. This is just a small subset of the results that we have in the paper. I'm going to show the results where we train with two different reward functions. The first one is moderately accurate, has 70% accuracy, and the second one is actually perfectly accurate, but has low reward. It induces low reward variance. And this is over a standard setting. It's a 3 billion parameter language model, a data set that contains questions of the type that people ask ChatGPT. And what you can see here is that despite the fact that the red proxy reward function is perfectly accurate, it leads to substantially slower increase in the ground truth reward, okay, because it induces low reward. Yes.
Why should we care? Because if humans do not see the difference by a lot, so it should not be improved.
So you can see the difference. This can be a matter of how many steps you need to train, or whether, like with the given budget that you have, whether you will even improve at all. So it is something that can matter, especially given like how large these models are and how expensive RL on them is to do. Yeah, any amount of steps it can save can matter a lot.
Maybe I don't understand something, but if I take a perfectly accurate proxy, for example, the ground of reward, it has some variance. If it's low, how can I beat it? You understand my question?
Yes, good question. And we're going to see a case in the next part of the talk where even if you have the ground truth reward, it's not the best to do. Here I'm just talking about accuracy. So even a perfectly accurate reward function, it's not necessarily exactly the ground truth. But we're going to see that even if you have the ground truth, it's not necessarily best. Right. There are cases where you should deviate to do better.
Right. For the perfect accurate model, your argument was that it will converge much slower, right?
Yeah.
Here it almost seems like it converged to a worse solution.
Right, so it depends on how much you run this. We have other experience with smaller models. In the end, if you run it for infinite time, it will be better, right? So it depends on the regime. So usually, if you're less accurate, you will saturate sooner. And if you train for a very long time, you may even cause reward hacking. In that sense, if you have the ground truth reward function, that's the safer thing to do. But sometimes you will never see this because it takes too long to optimize to see this. So in other cases, indeed, you can see that sometimes it will surpass if you train for long enough. So it's not exactly that it's converged, but just like it's getting really slow here. It's getting stuck, but it's not. Like if you train it for enough, it will escape. Usually. Okay, so this is why, at least one reason why more accurate reward functions are not necessarily better. And this is because the connection between reward variance and optimization. I'd also like to highlight that this has practical applications. Okay, reward variance, it depends on three factors. The first, which is what we mostly focused on, is the proxy reward function. But notice that it also depends on the data, on the prompts X, and the language model, the policy pipe data. And through these dependencies, it can shed light on other aspects of this policy grain pipeline and give us insights about what we should do in practice. For example, if we focus on the language model, then we find empirically that doing an initial supervised fine-tuning phase. This means that you collect some labeled data set and train your language model to directly produce these outputs, which are at least moderately okay. Then we show that this can lead to a substantial increase in the reward rates. Okay, through our theory, this implies that you're essentially finding a better initialization for policy gradient, and this can help explain why this is often beneficial in practice. Okay, this is somewhat of a common thing to do, to have some initial supervised fine-tuning phase using labeled data before you run policy gradient. And this can also give you quantitative guidelines to when it should be necessary or not by looking at the reward variance. Yes, there are questions.
Where do you use supervised fine-tuning in the variation in the learning process?
So usually before RL, before policy gradient, often people do some supervised fine-tuning.
Yeah. So the pre-training.
Yeah, you do pre-training, then you have sometimes, it depends on the task and where, some supervised fine-tuning, and then you do policy gradient methods.
So you're saying you actually add a second layer, like a layer in between?
It's usually, the post-training involves other components, not just reinforcement learning, and one of them is doing supervised fine-tuning. And oftentimes it comes before policy gradient. It really depends on the task and how you did pre-training. Yeah, it can vary. Right, from the data perspective, then follow papers have used this relation between reward variance and optimization to design new data selection algorithms. Okay, the idea is that you can train on prompts that enjoy a higher reward variance because you're going to learn more effectively over time. Okay, and you can try to do different curriculum. And also, if you go back to the perspective of the reward function, there have been works that propose new reward transformations and policy gradient methods based on our theory to try and improve optimization. And the reason I'm showing this is that this all goes to demonstrate, at least in my belief, reward variance is a key property for successful policy gradient optimization. Okay, it gave us one reason for why more accurate reward functions are not necessarily better. It can also help us identify optimization issues. If we see that for many prompts in the dataset, the reward variance is low, it will tell us that we're likely not going to increase the reward over them by that much. And beyond that, it can also be useful for developing new algorithms. And I believe that we're just scratching the surface in terms of what we can do here. Okay, so this wraps up the first part of the talk. And now what I'd like to talk about is based on another paper, a recent one, which was led by Shuning Shang and Hubert Strauss from Princeton. And this is going to talk about how, okay, aside from reward variance, which gives us a necessary condition on what makes a good reward function, it's also important to notice that not all deviations from the ground truth reward are the same. Okay? A bit about terminology. So here I'm going to use reward error to refer to cases where the proxy reward function and the ground truth disagree. Okay, this can be on one or more input-output pairs. And due to the risk of reward hacking that I mentioned already, reward errors are conventionally viewed as harmful. Okay, and the type of reward error that leads to this reward hacking is if you assign a high proxy reward to an output which is actually bad. It has low ground truth reward. So you're maximizing the proxy reward, and you're reaching some output which has a high proxy reward, but actually it is not good under the ground truth. But aside from harmful, what we prove is that reward errors can also be benign, and perhaps more surprisingly, they can even be beneficial. Okay, we categorize different reward errors according to how they affect the increase in the ground truth reward. Okay, so when I say that a reward error is harmful, it means that it either slows down optimization or leads to a decrease in the ground truth. Benign means that they don't matter much, and beneficial means that they can accelerate the increase in the ground truth reward beyond what we can get if we optimize directly the ground truth. Okay, and we do this categorization by analyzing which outputs attract probability under policy gradient. Okay, until now, we talked about if you have low reward variance, you're in a very flat area. And now we're going to talk about, okay, which directions does policy gradient take and how that affects whether deviating from the ground truth reward is beneficial or not. Okay, so I'm going to start with a warm-up. This is going to be two types of benign errors. They're going to be quite intuitive, not surprising, but I think it's still good to put them out there to get a good picture of what is going on. And the first one is going to be that outputs with low proxy reward, they don't really matter much. They don't attract probability, which makes sense, right? And the way that you can see this is by looking at how the logits evolve during training. So we're going to look at the logit of some output y, and this is going to be for a linear softmax policy. And the time derivative of this logit, okay, how it evolved through training, it depends on two factors. Okay, this is just a simple calculation, nothing special going on here. But what you can see is that it's that probability of the output multiplied by the advantage of it. Okay, this is the proxy reward of the output minus the current expected proxy reward. What we can see from this is that what determines whether the logit increases or decreases is the advantage. Okay, if an output has a negative advantage, okay, a proxy reward which is lower than the current expected reward, then its logit will decrease. It will not attract probability. Okay, this means that if we have some output, which is not the optimal output, it's not what we want to learn anyways, and we incorrectly assign it a very low reward, then it doesn't matter much. Okay, it won't attract probability, and yeah, maybe it's not problematic. Now, the second type of benign errors, which again is going to be quite intuitive, is that if we have outputs which have very low probability under the current policy, then it doesn't really matter which rewards we give them. Okay, and again, we can see this from this logic dynamics. Okay, if we look here, you see that if the probability of the output is low, then it will evolve very slowly, and it will also affect other outputs very minimally. And because of that, what this suggests is that, yeah, if we make some mistake on an output which has low probability, we won't really pay for it. And you can formalize this. Okay, you can show that for any optimization time and approximation level, epsilon, if the proxy reward function, the ground truth, differ only on a set of outputs that has low probability, and of course, it needs to be lower for the longer you train and depending on epsilon, but what you get is that the total variation distance between the policy that you would have gotten if you train with the proxy reward function and the policy that you would have gotten if you would have trained with the ground truth, it's up to epsilon. Okay, so essentially it doesn't matter if you train with the proxy reward function or the ground truth here, as long as they only disagree on low probability outputs. Again, it's quite intuitive, but this lets us know that, okay, if our reward function is incorrect on outputs which are very of low probability under our policy, okay, this depends on our policy, then yeah, we shouldn't care about it too much. All right, and now after this warm-up, we can get to the more interesting, at least on a technical perspective, I think in terms of how surprising the result is, of looking at, okay, what is the beneficial error? When should we deviate from the ground truth? So what we saw is that outputs with low proxy reward or low probability, they don't attract probability during policy gain. So where does the probability go? And okay, we can go back to our favorite equation. I swear this is the last time that I'm going to put it up. And you can see again that it's this product between the probability and the advantage, right? So what will attract probability is an output that has positive advantage and is likely under the current policy. Okay, and what this implies is that the policy gradient doesn't necessarily point towards the optimal output. Okay, you can have mediocre outputs which are better than what you're currently doing, but still not optimal. And if they're very likely, then actually policy gradient will be drawn towards them. Okay, in a picture, if you're here, and here is the optimal output, and this is some mediocre output which has higher probability currently under the policy, then hopefully we would have wanted the direction of the gradient to be towards the optimal output. Okay, and I'm talking here about the expected gradient, okay, the true gradient. But actually where it points to, it can point towards this mediocre output instead. And this phenomenon, it's actually not new. It was identified by a paper in 2020 by May et al. And it was known that softmax policy gradient can have this weird behavior where the gradient doesn't point towards the optimal output. But the open question was, okay, how severely does this affect optimization? How severely does it delay how fast we increase the ground truth reward? And you can imagine two worlds. Okay, in one world, this is a mild delay. Okay, initially the gradient points towards the wrong direction, but then it quickly corrects course and you reach pretty fast the optimal output. But in the other world, maybe you go towards the mediocre output, then you get stuck around it for a long while, and then it will take you a long time before you eventually reach the optimal output, if at all. And what we're going to see is that this can cause a severe delay. Okay? Specifically, suppose that for some input x, y star is going to be the optimal output. Okay, this is the output with the maximal ground truth reward. And suppose that we also have some mediocre output whose ground truth reward is better than what we're currently doing, but it is not as good enough. Okay, it's not as good as y star. And as a baseline, as a comparison, let's say we have some proxy reward function, which is identical to our ground truth reward, but it incorrectly assigns a minimal reward, a low reward, to the mediocre output. Okay, so how do these reward functions differ in terms of optimization time? Well, it turns that the time it takes to achieve near optimal ground truth reward can be arbitrarily larger if we train with the ground truth reward directly, okay, compared to training with the proxy reward function. Okay, and what controls this gap is the relation between the probability of y star and the mediocre output. Okay, the larger the probability of the mediocre output is relative to the probability of y star, the longer we will get stuck around the mediocre output, and effectively using the proxy reward function, which in some sense is incorrect, but it does lead to faster increase in the ground truth reward. And the idea behind the proof is, okay, we show that under the ground truth, indeed, if you train under it, first the policy will go towards the mediocre output, and we quantify how much it concentrates probability mass on. And we show that the policy becomes near deterministic, right? It gives probability almost 1 to the mediocre output. And what happens then is that the reward variance collapses, right? If the policy is near deterministic, then it doesn't matter even what your reward function is at this point. The reward variance will always be near 0. And as you might recall from the first part of the talk, when this happens, the gradient vanishes and you stop. Okay, so what you have in this trajectory is that you first go towards the mediocre output, get stuck here, and then eventually you escape and you can converge. On the other hand, if you use the proxy reward function, which eliminates in some sense this mediocre output, you just directly go to the optimal output.
You need to put that point right where
This, yeah.
exactly.
Yeah, I didn't plan it ahead of time. Yeah. Okay, and what we can see from this is that this gives us a type of beneficial error. Okay, let's say our ground truth reward has some output which is of mediocre quality, then it may actually be better to assign it a low reward and deviate from the ground truth to get a faster increase of the ground truth reward. Okay, so now we can take a step back and look at the different rewarders that we discussed to get a full picture of the categorization. And the first error that we talked about is the most well-known one. Okay, this is if you assign a high proxy reward to an output which is actually bad, yeah, this is problematic. This can lead to reward hacking, and this is not desirable. We then saw that, unsurprisingly, okay, if you have outputs which have low probability under the policy, or you assign some output a very low reward and it's not really the optimal output, then this is benign. It doesn't matter much. And then we saw that there are some cases where you should deviate from the ground truth. Okay, if the ground truth reward gives some output, a mediocre output, which is likely under your policy, it may be better to just assign a low reward instead, and then you prevent your policy from stalling around it. Okay, this is a theoretical categorization of rewarders, and it has some nice practical applications that I'd like to show now. And the first one is that it can help us develop new measures to evaluate proxy reward functions. Okay, recall that in the context of language models, alignment of language models, accuracy is the measure that people usually use. And it treats all incorrect output rankings as equally harmful, right? We have some fixed data set, and any incorrect ranking matters the same. And as we saw, this is a bit naive, right? I mean, intuitively, not all errors are the same, and we just showed this, that some of them can be benign or even beneficial. And what we propose is just some simple tweaks to this equation, and to get a better measure that is more predictive of which proxy reward model will work better. And the first straightforward thing that you can do is, okay, let's weight each example by the probability under the policy, right? If these outputs are not probable anyways, they won't really matter for policy grain optimization, and we shouldn't really count that mistake too much. Okay, so this is one very straightforward change. The other is that, okay, if we have an incorrect ranking, let's say y minus has a higher reward than y plus, then maybe we can still forgive this error if the reward of y minus is lower than the current expected proxy reward, right? Because what this means is that despite the fact that we didn't rank correctly these outputs, policy grant will not learn to produce y minus anyways, because it's worse than what we currently have under the proxy rule. So maybe this is also benign, in some cases maybe can be beneficial, so we shouldn't really count that as an error. Now these are the two simple modifications that we make, and this is what you can call maybe a harm-aware accuracy measure, okay, because it depends on the policy and which errors are likely to be harmful or not for it. And then you can check whether this measure is more predictive of which proxy reward model is better compared to standard accuracy. And so we train multiple different language models, each one of them using 13 different reward models on a standard data set, okay, that contains questions of the type that people ask language models. And what you see here is the correlation between the increase in the gram truth reward and the actual performance of the language model compared to the measure itself, accuracy, or the harm-aware accuracy. The higher the correlation, it means that the more predictive the measure is of which reward model works better. And as you can see, pretty much across the board, except for this last case, we have a significant advantage compared to the standard accuracy measure. And here, okay, accuracy is still better, but the gap is a lot smaller compared to the other cases. And this shows that by making simple modifications to how people currently evaluate reward models, we can do better. But it's worth highlighting that we're still very far from having a robust way to evaluate reward models. So this is an open challenge, which, yeah, I don't think anybody today, if you give them a list of 10 reward models, can tell you which one will work better without running policy grid, unfortunately. You can see that we're still below 0.4 correlation. There are cases where you do get higher correlation, but yeah, there's no robust measure for evaluating proxy reward functions, which shows that there is much more work to be done. Okay, and the second application is in domains where you have verifiable rule-based rewards. And these are domains such as coding and instruction following, where often the output needs to satisfy multiple constraints to be correct. Okay, for example, in code, then your model needs to produce some function, and then you evaluate it using unit tests, and if it passes all the unit tests, then yeah, that output is considered correct. Instruction following is another common benchmark that people evaluate language models with. You give them some prompt, and you can also give them constraints. Okay, you want the prompt to be, maybe you want it to contain a number, you want it to be short, under 40 words, and then you can verify that it exactly produced outputs that follow these constraints. Okay, and then you can measure this, and if it satisfies all constraints, then you can consider it as correct. And in these cases, the question that arises is whether we should reward partially correct outputs. Okay, one paradigm can be, yes, let's give a reward of 1 to fully correct outputs, some intermediate value to outputs that are partially correct. Let's say they satisfy only one of the two constraints, and okay, 0 to others. The other potential paradigm can be to give only binary rewards. Okay, only fully correct outputs receive a reward of 1, everything else a reward of 0. Okay, which one should we choose? Intuitively, partial rewards should be helpful because they give us more information. Okay, they tell us that maybe this output is not perfectly correct, but okay, it got something right. But according to our theory, okay, if the language model is much more likely to produce a partially correct output than a fully correct one, then what may happen is that may actually learn to only produce these partially correct outputs. Okay, these are the mediocre outputs that we had in the analysis. Policy grid may be attracted towards these outputs and get stuck around them and stall and never learn to produce fully correct outputs. And we show that this can be the case, okay, in pretty much standard settings. We take language models and train them over a data set where each prompt contains a pair of constraints, and they're specified in the prompt of the type that I showed you before. Okay, for example, please include a number in the answer. And here what I'm going to show is with a Quen model, and we take the constraints from a standard instruction following benchmark. And here's the results over one of the data sets for the two paradigms of the reward function. Here we train with partial rewards. And what you can see is that when there is a very big gap between the probability initially of satisfying one constraint, you can see that this one starts from around 0.2, and satisfying both, which here is a lot lower because satisfying the other constraint is small, then what can happen is that we will only learn to produce outputs that satisfy one of the constraints, and then we get stuck. Okay. On the other hand, if we only reward fully correct outputs, okay, initially it may take us longer to get any signal, but then once we get enough examples that are fully correct, then the model will quickly learn to satisfy both. So we actually learn the correct objective much, much quicker, even though we don't give partial rewards. And it's worth contrasting this with the other case where, okay, if there's no big gap in learnability, okay, in the initial probability of these constraints, then both designs can work well. It's worth saying that there are cases where giving partial rewards can be helpful. Okay, I'm not saying that they're never helpful. It's just that perhaps in contrast to what people would believe, there are cases where rewarding partially correct outputs can be harmful. Okay, so it's not that always we should do this. It depends on the setting, on the language model, on the task at hand. All right, so now let me conclude and
Yes.
yeah, I have a question. Yeah, sure.
On the other hand, rewarding partially correct outputs increases the variance of the policy.
Oh,
right?
yeah, that's great. So in general, also with the theoretical result that I showed, right, you might wonder, I showed that using proxy reward function can be better than the ground truth. And is this just due to the reward variance? So actually, no. So what happens is that initially the ground truth reward actually has a higher variance than the proxy reward that eliminates the mediocre output. And this is also the case here, right? Because you're optimizing faster the partially correct one. Here you're stuck. But the gradient doesn't point in a good direction. So what happens is that under the ground truth, you're not stuck initially, but you go towards the mediocre output, and then you get stuck around it for a longer time because the reward variance collapses. And if you only here reward fully correctness, initially your reward variance is lower, so you're stuck for longer here, but when you escape, and you escape faster, you go directly to where you want to. Yeah.
This kind of invites a curriculum somehow.
Yes, yes. So there are
Starting with that and then
yeah, exactly. So there are empirical papers that what they do is, okay, let's say you get exactly zero. You never have fully correct output. So obviously using binary rewards will not work. So people have shown that what you can do, you can first do partial rewards, and okay, you learn maybe one of them, you get stuck, but now satisfying both will not be exactly zero. And then you can transition to binary rewards and then you'll learn. Yeah, exactly.
There are no theoretical words characterizing this trade, like
Time like doing this curriculum? No. There's still much more to be done. Okay, so to conclude, what we talked about today is what makes a good proxy reward function, specifically for policy grid methods. This was our focus. And we began by looking at the role of reward variance. Okay, we saw a necessary condition for a good proxy reward function. It needs to induce sufficient reward variance for us to be able to optimize it efficiently. And this gave us one reason for why more accurate reward functions are not necessarily better. And we also discussed practical applications for data selection and policy grid methods. We then moved on to see how different deviations from the ground truth reward affect optimization differently. Okay, conventionally they're viewed as harmful, but they can be benign or even beneficial. Where the interesting mechanism here behind the beneficial errors is that policy gradient can get attracted to mediocre outputs and can stall around them for a long time. And this has implications both for how we evaluate and design proxy reward functions. And to conclude with a takeaway, going forward, then our results, they shed light on what makes a good proxy reward function, but indeed it doesn't tell you the complete picture, right? I still can't tell you, give me a ground truth reward, give me your policy. I don't know what is the best proxy reward function that you can use in some sense. So there's still much more work to be done here. And perhaps a takeaway that I think it worth like sending you home with from this talk, if you remember one thing, is that this line of work, it highlights that the effectiveness of proxy reward functions, it can't be assessed solely by how much they deviate from the ground truth. Okay, it heavily depends on this interaction between the proxy reward function, the policy that you train, and the learning algorithm, which here we fix to be policy grid. And it is only getting more important to better understand this interaction, given the fact that these days AI agents are being trained on environments that are increasingly complex, mostly using proxy reward functions. And I think that we should understand this better. And that's all I had for today. So I'd like to thank my collaborators at Apple and Princeton, and especially Schuning and Hubert, which led the last project that I talked about with the reward error categorization. And thank you for your attention.
יש עוד שאלות? So the difference between supervised fine-tuning and policy gradient RL is it really well defined? Isn't there? Couldn't you do supervised fine tuning on the preferences, for example?
Yes, so there are actually this question is exactly what led me to this line of research. And on a technical perspective, you can just consider it's two types of objectives, and you can do supervised fine-tuning on preferences. There are methods. The most well known is called DPO, direct preference optimization, and it gives you a different landscape. And indeed, it doesn't suffer from these optimization issues, but it has its own issues. And actually, the conventional wisdom in practice these days is that it doesn't work as well as these online, on-policy grade methods. Yeah.
Do you have any idea what's the state of the art? I know ChatGPT how does it compute its reward, given its binary response?
So nobody knows it unless you work there, and then you can't tell. I think in the academic literature, there's a lot of focus on designing sophisticated proxy awards. For example, using language models that give you rubrics of. It's very hard to produce a robust reward function, but maybe if you produce different criteria, and you can also evolve these criteria using a language model in some loop, and then you can give like more fine-grained kind of guidance to the model. There are also other methods of getting a reward function from the log probabilities of some feature model. It's called on-policy distillation. It has gained a lot of popularity in recent, I think, months. Yeah, but I don't think that there's like a standard method that everybody knows. Okay, this is how we should design or use proxy reward functions for our task.
But is usually the triplets preferences that's typically the data that's used, or is it?
So for alignment, for the tasks of alignment, yes, you can use also more than two outputs, but this is kind of a standard basic setting. But this is also relevant for tasks like solving math problems, coding, and more broadly. But yeah, for alignment, then yes, it usually is pairs of. Like for the math and coding, you don't usually train a reward model. You have rule-based rewards that you design. Okay, is the final answer to this math question correct?
Yeah.
שאלות? תודה רבה לנועם.